Welcome to the Last Economy podcast, a guide to the age of intelligent economics. Today, we are doing a really crucial deep dive. We're looking at Chapter 7 of the book. It's called The Generative Engine. Now, in our previous discussions, we sort of established the core physical why, didn't we? The reason behind this new economy. That deep existential push for intelligence to be the main force fighting entropy, creating order where there's usually decay.
Exactly. The why.
But knowing why isn't much use if you don't understand how, right?
That's precisely it.
Yeah.
If the last chapters were the philosophy, this one. This is more like the engineering manual. For you listening right now, the goal here, the mission of this deep dive, is really to shift how you see economic activity.
Yeah.
Fundamentally.
Okay.
We need to move away from thinking about the economy as just this messy, unpredictable thing driven by, human psychology and scarcity.
Right, the traditional view.
And start seeing it for what the book argues it is, a massive, continuous computational process.
A computational process. And the book claims it's giving us the manufacturer specifications, like the rules for how reality actually persists, how it works.
That's the promise.
Right.
Stripping away the politics, the ideology, all that noise.
And grounding it in physics, computation.
Exactly. Physics and computation. So value creation based on those fundamental principles.
Okay, let's dive in then. The fundamental algorithm. What drives this generative engine? The book says the core mechanism is this process of guided, iterative refinement. And it has a scientific name.
It does. It's known as the diffusion model. And honestly, it's brilliant. A masterpiece of counterintuitive thinking. Because this generative process, making something new, something complex, seemingly out of nothing, it isn't some mystical flash of inspiration.
No magic involved.
Computationally speaking, no. It's a process. It's about taking chaos and systematically removing it.
Denoising it.
Denoising chaos.
We can picture this really well using a technique from modern AI. The diffusion model, as used in image generation, is a perfect analogy. Right, I've seen those AI images. So let's unpack that analogy.
Yeah.
The book argues that creation, whether it's a picture of a cat or, a stable economy, follows two key steps.
Two crucial steps, yes. Step one is what they call the forward process, and this is the really mind-bending part.
Okay.
This step is basically a perfect mathematical simulation of the second law of thermodynamics.
Universal decay. Entropy.
Exactly.
Yeah.
Entropy. You take something perfectly ordered, like a really sharp, clear photo.
Got it. A cat photo.
A cat photo, sure.
Yeah.
And you systematically wreck it. You add a tiny, precise amount of random noise, just a little bit. Then you do it again and again, hundreds, maybe thousands of times. Each step adds a bit more noise.
On the whole.
Until the original picture is completely gone, obliterated. All you're left with is static, featureless noise, pure high-entropy chaos.
Wow. So the intelligence, the AI, first learns how to destroy things perfectly, systematically.
It has to.
But why? Why learn destruction before creation? Seems backwards.
Well, think about it. It defines the problem. It maps out the terrain of chaos. If you don't know the exact mathematical steps it takes to turn order into chaos.
And you can't figure out how to reverse it.
Precisely.
Yeah.
You can't find the mathematical inverse. The forward process calibrates the whole system. It teaches it the reality of decay, the thermodynamic cost of disorder, you could say.
Okay. That makes sense. It maps the path to chaos, which then allows for the magic, the reverse process.
Yes. This is the generative part. This is creation. The AI learns how to start with that field of pure static, that random noise.
The endpoint of the forward process.
Right. And guided by an instruction, we call it a prompt, like a photo of a cat sitting on a chair. It starts incrementally reversing the destruction, step by step. Hundreds of small, targeted, intelligent steps.
Doing what exactly?
Removing the noise. Each step takes away just the right amount of noise, guided by the prompt. And slowly, out of that statistical static,
The cat appears?
the coherent image is revealed. The cat on the chair. The system is literally, computationally, forcing order into existence out of chaos.
That is genuinely amazing. And here's where the book makes that huge leap, right? From AI making pictures to, well, everything else. The global economy. Let me read that first quote because it really captures this core idea from the book. This is not just a clever trick for making pictures. This is the fundamental algorithm for creation.
Boom. Right there. That
What's
one
that?
sentence. It completely reframes what the economy is and what it does.
So it's not just markets and trade.
No. It's this generative process, this diffusion model in action, but on an unimaginable scale. The economy is performing that reverse process.
But instead of denoising pixels in an image.
It's denoising possibilities. Think about the input. It's pure chaos, right? Infinite human desires,
Yeah.
limited resources, technological hurdles, geopolitical friction, climate change, pandemics, all that uncertainty.
That's the static, the noise.
That is the statistical static the economy starts with.
And so, every single economic action, like me buying coffee, or a company investing in a new factory.
Or an entrepreneur having an idea, someone making an investment, a government setting a policy. Every transaction, every decision.
It's one tiny step in this huge calculation.
One tiny incremental denoising step, part of this massive distributed computation.
Wow.
Every single economic actor, whether they realize it or not, is constantly, implicitly asking a question.
Which is?
Okay, given the mess we're in right now, this chaotic present, what's the single smallest, most efficient thing I can do right now to move the whole system just a tiny bit closer to the ordered, predictable future I want?
Or that serves my interest, presumably.
Which in aggregate pushes towards some kind of order, this relentless distributed drive. That's what generates coherent things like prices, stable supply chains, functioning companies. It's order emerging spontaneously from all these decentralized efforts.
It almost sounds, miraculous.
Right.
Or like an invisible hand, but described computationally.
It does feel like that, but the book argues it's not faith, it's physics. It's relentless, it's non-voluntary in a way.
And the prompt, the guiding instruction for this whole economic denoising process.
That's the physical imperative we talked about before, the drive inherent in intelligent systems to be the most efficient engine of order possible, to minimize the thermodynamic cost of creating and maintaining that order.
So the universe itself is pushing towards efficiency and order through intelligence.
It's like the universe's most complex calculator, you could say, constantly running this denoising algorithm. And this isn't just a nice metaphor. This brings us to the really deep mathematical reality behind it all. It has a precise technical definition.
Which describes the actual physics of how the economy moves and changes.
Exactly.
Okay, and that definition leads us straight to the second really impactful quote you picked out. This one introduces the core mechanics, the technical terms.
Yes, this quote gives the proper name for the engine driving this whole generative denoising process. It says, the technical name for this process is stochastic gradient descent, SGD, on a geometric manifold. But the intuition is now clear. The economy is a generative engine, a machine for turning chaos into order, guided by the compass of intelligence.
Stochastic gradient descent on a geometric manifold. That's a mouthful.
It is, definitely.
Let's spend some real time unpacking that, because those terms, SGD, geometric manifold, the book says they're like the constitution for this new economic physics.
They really are.
We get the generative engine part. Now it's a machine making order from chaos.
Check.
And the compass of intelligence, that physical drive for efficiency we just discussed.
Double check.
But what on earth is this geometric manifold?
Okay, imagine. Imagine the space of all possibilities. Everything the economy could ever possibly be.
Whoa.
Every possible price for every good, every conceivable technology, every possible social structure, every regulation, every configuration of firms and resources. Everything. That entire infinite landscape of potential economic realities, that's the geometric manifold. It's like a multidimensional shape, incredibly complex, representing every state the economy could be in. Yeah. It's the map of all possible economies.
That sounds impossibly vast, infinitely complex. How does the actual economy, made up of billions of people doing random stuff, how does it navigate that map? How does it find its way?
That's where the gradient descent part comes in. SGD, stochastic gradient descent.
Okay, gradient descent.
Imagine that manifold, that landscape of possibilities, as a huge, complex mountain range with peaks and valleys.
Right.
The goal of the economy, driven by that compass of intelligence, is to find the lowest possible valley, the point of maximum stability, maximum predictability, the lowest energy state, thermodynamically speaking.
Lowest cost. Maximum order.
Exactly. Gradient descent is just the mathematical process, the algorithm for always heading downhill, always moving in the direction of the steepest slope downwards.
Okay, always seeking the nearest valley, the closest point of stability.
It's always trying to find a better, more ordered state by taking the most obvious downhill step available right now.
But wait, if it only follows the steepest path right in front of it, doesn't it risk getting stuck? Like finding a little dip, a small valley, and thinking, okay, I'm stable here, even if there's a much, much deeper valley, a way better solution just over the next hill.
That is the critical question. You've hit on the key problem with simple gradient descent.
It gets stuck locally.
Exactly. A purely deterministic, follow the steepest slope gradient descent would get stuck in what mathematicians call a local minimum. It finds a pretty good solution early on, settles in, and stops searching, stops learning.
Even if a vastly better, more stable, more globally optimal reality is possible.
Correct. It thinks it's reached the bottom, but it's just stuck in a pothole on the side of the mountain. And that brings us to the most important word in the whole technical name, stochastic.
Stochastic, which means random, involving randomness.
Bingo. Stochastic means involving a random variable. It's not purely deterministic. Why does the economy, this engine trying to find perfect order, need randomness baked into its core algorithm?
That seems like the opposite of what you'd want.
You'd think so. But the randomness is the key. It's the engine of exploration.
How so?
The stochastic part means the steps the system takes downhill aren't perfectly straight down. There's a little bit of jiggle. A small, controlled amount of randomness or noise injected into each step.
So it doesn't just go straight down the slope.
Sometimes, because of that randomness, it might take a step slightly sideways, or even a tiny step uphill, away from the immediate steepest path.
Taking a step uphill, why would it do that?
Because that little random nudge, that small burst of uphill energy, might be just enough to pop it over the ridge of that local minimum.
Oh, to escape the pothole.
Exactly. It escapes the local trap and can then continue searching the wider landscape for the truly global optimum, the deepest valley, the best possible stable reality it can find.
So, the chaos we see in the economy, the unpredictability, market swings, sudden shocks, people making weird choices, that's not just noise messing things up.
It's not just a bug. The book argues it's a fundamental feature. It's the necessary stochastic element. It's the randomness that prevents the entire generative engine from getting permanently stuck in some stagnant, mediocre, suboptimal state.
Wow. Okay. So if the system were perfectly predictable, perfectly efficient in the short term,
It would find a solution, but it would lose adaptability. It would never find the best solution over the long run. The randomness, the chaos, fuels the continuous search.
so the economy is this physical computation, constantly learning, constantly iterating, using randomness to explore and find better, more stable, lower entropy states.
That's the core idea. And it means the economy's health, its ability to persist, isn't about political ideology. It's about adhering to these fixed physical laws of computation. It's a relentless mathematical pursuit of stability.
Okay, and if it is a physical computation grounded in physics,
Then it must obey certain physical laws, non-negotiable ones.
the manufacturer's specifications you mentioned earlier.
Exactly. We're shifting now from how the engine runs the SGD on the manifold to the absolute must-follow operating constraints. The rules a living, persistent system has to obey if it doesn't want to just decay and fall apart.
3 fundamental laws for persistence.
Derived directly from physics, from the need to minimize computational cost and thermodynamic waste over long periods. They're the constitutional constraints for vitality itself.
All right, let's tackle the first one, the law of flow.
The law of flow. This one's got 2 parts, really.
Okay.
First, value must be conserved. What does that mean? It means the system needs an accurate model of reality.
Like good accounting.
Fundamentally, yes.
Mm-hmm.
You can't just consume your capital, whether that's money or natural resources or social trust, without correctly accounting for the cost. If you pretend costs don't exist, your model of the world diverges from actual reality.
And when your map doesn't match the territory.
You're guaranteed to fail, catastrophically, eventually. So conservation, accurate modeling is step 1.
But just conserving isn't enough.
Nope. That's the second equally crucial part. Value must also circulate. It has to flow vigorously.
Okay, hang on. If I'm thinking like a traditional economist or just, a person trying to survive, isn't my goal to accumulate resources? To
Yeah.
hoard them, protect myself from future uncertainty?
That's the standard intuition, yes.
So why is hoarding, accumulating capital without actually using it or circulating it, considered a physical failure state under this law?
Because hoarding literally stops the generative engine from learning. It jams the gears of the SGD.
How?
Think about what capital is. Money, information, materials, skills. It's all essentially crystallized predictive power. It represents potential energy to shape the future.
Okay.
If that capital is just locked away, sitting idle in a vault or a database or someone's head, it's not doing anything. It generates no new data for the system. It tests no new predictions about the world. It can't participate in that ongoing process of stochastic gradient descent, exploring the manifold.
So flow is needed for the learning process.
Flow is a physical necessity for intelligence. Learning requires interaction, exchange, feedback, taking risks, putting capital into motion, accumulation without circulation. That's thermodynamic stagnation pretending to be wealth. It stops the search for better states.
And the book gives a really stark historical example of this. The collapse of the city of Cahokia around 1350 AD.
Cahokia. Yeah, it's a fascinating and tragic story. Located just across the Mississippi from where St. Louis is today.
A huge city for its time, really.
Monumental.
Hmm.
And it wasn't isolated. It was the central hub for this vast trading network, covering a huge chunk of North America, Great Lakes down to the Gulf Coast.
And its success was built on
Flow, purely on flow. The constant circulation of goods, materials, information, people, ideas across enormous distances. That network, that circulation kept the system vibrant, adaptable. Its capital was always in motion, constantly updating Cahokia's model of its world.
But something changed. The archaeology shows it was abandoned pretty suddenly. What happened?
Well, leading up to the abandonment, around the 14th century, the evidence suggests that flow started to constrict, to seize up. Those big open trade networks seem to have fragmented. And critically, wealth resources, prestige goods, started to concentrate. It became localized within the city, hoarded by elites, often physically separated behind walls or in specific precincts.
So it shifted from a flow-based economy
To an accumulation-based one,
Okay.
exactly. And when the resources stop circulating, got siloed away, the system effectively stopped learning. It couldn't adapt anymore. Maybe climate shifts happened. Maybe internal social stress built up. We don't know the exact trigger.
But because the flow stopped, it couldn't respond.
It lost its resilience, its ability to compute solutions. Within maybe a generation, the whole place was empty. A massive, complex city collapsed, not because of invaders, but seemingly because its internal circulation failed. The model diverged from reality. The engine seized.
That's a powerful warning, especially today with debates about wealth concentration.
It's a direct physical consequence, according to this law.
Okay, that's the law of flow. What's the second non-negotiable constraint?
The law of openness. This one deals with how the system interacts with its environment, its boundaries. And honestly, this might be the single most uncompromising law imposed by thermodynamics on any living or complex system.
That sounds serious.
It is. To maintain its complexity, its low entropy state, basically, to stay ordered and alive, a system must be open.
Yeah.
Isolation over the long term is physically impossible. It guarantees failure.
Why?
Because a system needs to constantly do two things. It has to import low entropy energy and information from its environment. Think fresh resources, new data, new ideas, things that allow it to maintain or increase its internal order.
Okay, import order.
And second, it must export high-entropy waste back out, the byproducts of its internal processes. Heat, waste materials, outdated information. If it can't do both, it chokes. Closure means inevitable decay and stagnation. Systemic death.
But hang on. We hear a lot today about countries wanting to decouple, build walls, achieve self-sufficiency, strategic autonomy. It sounds like they're seeking stability through closure. Why is that fundamentally wrong, according to this law?
Because the environment isn't static. That's the key. You seal your system off, yes, you might achieve perfect stability relative to your own internal state. You lock everything down.
Sounds good, right? Predictable.
But you simultaneously stop updating your model based on what's happening outside your walls.
Yeah.
You sever the inflow of new information, new energy. The cost of closure is the end of learning. You lock in yesterday's solutions, yesterday's tech, yesterday's understanding of the world, while the world outside keeps changing.
And the gap between your internal model and external reality just grows and grows.
Until something forces an update, often violently.
And the historical example here is Japan, the Sakoku period, the chained country.
The ultimate case study. For over 2 centuries, 214 years, from 1639 to 1853, Japan, under the Tokugawa shogunate, basically sealed itself off. Minimal contact with the outside world.
They achieved stability, though, didn't they?
Oh, incredible internal stability. They ended centuries of civil war. Society became incredibly ordered, predictable, fixed. If stability was the only goal, you'd have to say they succeeded brilliantly. For a time.
But the law of openness was ticking away.
Like a time bomb. While Japan was perfecting its internal rice-based economy and samurai culture, what was happening outside?
The Industrial Revolution.
Exactly. Coal, iron, steam power, new scientific knowledge, massive imports of low-entropy energy and information were transforming Europe and America. Japan, meanwhile, was exporting almost nothing informationally and importing almost nothing new. It wasn't just failing to export waste, it was starving itself of the inputs needed to keep its model current.
Until Commodore Perry showed up.
1853. Perry
Oh.
arrives with his black ships, steam-powered warships, modern cannons. The technological gap was immense, devastating. The shock forced Japan to confront just how far its internal model had diverged from external reality.
And the price of that long closure was...
A rapid, wrenching, nearly catastrophic forced modernization, the Meiji Restoration. It highlights that openness isn't just a good idea or a political choice. It's a physical requirement to fight entropy over the long haul. You have to stay connected to reality.
Flow and openness. Got it. That leads perfectly to the third law, doesn't it? The law of resilience. Because if you are open, if you do have flow, you're constantly dealing with that unpredictable external environment. Shocks will happen.
Exactly. And that's where the traditional focus on pure efficiency breaks down.
Right, because industrial thinking for the last century or more has told us efficiency is king. Streamline everything, eliminate waste, eliminate redundancy, get the leanest possible system.
That's the dogma. Optimization equals success. But this third law says, not so fast. It directly challenges that. Let me read the third key quote here. The law of resilience. Diversity creates stability. A system optimized for a single predictable future is a monoculture. It is highly efficient, but catastrophically fragile.
A monoculture. Highly efficient, but catastrophically fragile. So, diversity isn't just, a nice to have, a social goal.
The book argues it's a core physical strategy. It is resilience. It's the system's insurance policy against a universe that is fundamentally unpredictable.
How does diversity provide that insurance?
Think about it. When you optimize purely for efficiency based on current known conditions, what do? You strip away everything that isn't immediately useful right now. You eliminate backup systems, alternative approaches, redundant skills, different suppliers, because they seem wasteful in the present moment.
You create a monoculture, one perfect way of doing things.
Yes, and that system might perform brilliantly as long as the conditions stay exactly as predicted, but the moment an unpredicted shock arrives, a new disease, a climate event, a technological disruption, a war,
The system has no alternative, no backup, no other way to function.
it breaks. It's brittle, catastrophically fragile. Resilience, on the other hand, is defined by the system's ability to take a hit, to absorb a shock without collapsing, without losing its fundamental function.
And diversity is a mechanism for that.
Diversity is the mechanism. Having many different varieties, many different pathways, many different skill sets, multiple sources. It's like holding an option portfolio.
Options, like in finance.
Exactly like that. Some of those options might seem slightly less efficient today. They might look like redundancy, but they represent possibilities.
Yeah.
They ensure that when the unexpected happens, the black swan event, the whole system doesn't just shatter. One pathway might fail, but others remain.
So the pursuit of maximum efficiency actually creates fragility.
It trades resilience for short-term optimization, a very dangerous trade in an uncertain world. The high cost of that optimization is catastrophic fragility.
And the example the book uses is, well, it's almost comical if it weren't so instructive. Bananas. The great banana collapse.
Here's a banana. It's the perfect tragicomic illustration of this law.
How so? What happened with bananas?
Well, for basically the first half of the 20th century, the entire global banana industry was this incredible feat of optimization. It was built almost exclusively around one single variety of banana, the Gros Michel, Big Mike.
Why just one type?
Because it was seen as perfect. It had a thick skin, so it didn't bruise easily during long sea voyages. It ripened slowly and predictably. Apparently, it tasted fantastic. So the entire global system, plantations, shipping, ripening rooms, was engineered with ruthless efficiency around this one, known, predictable variable, a planetary monoculture.
Maximum efficiency, minimum diversity, performing beautifully.
Under the known conditions. But then the stochastic element inevitably arrived, the unpredictable shock.
Which was?
A fungus, a soil-borne fungus called Panama disease, Fusarium wilt, technically.
And because every banana plant was the same?
Genetically identical clones. The Gros Michel was propagated by cuttings, not seeds. So once the fungus appeared that could kill one Gros Michel plant, it could kill all of them. There was zero biological diversity, zero natural resistance within the entire global crop. The fungus didn't even need to adapt. It just ran rampant.
Just swept through the monoculture.
Wiped it out. The entire global industry collapsed in just a few decades. Billions of dollars lost. They had optimized for efficiency so perfectly that they had zero resilience when the unexpected happened.
And the cost of that efficiency. Total system failure. They had to completely re-engineer the whole thing, right? Switch to the Cavendish banana we mostly eat today.
Exactly. They had to scrap the Gros-Michel system and adopt the Cavendish,
Mm-hmm.
which is resistant to that particular strain of Panama disease. But most people agree it doesn't taste as good and bruises more easily. It was a massive, costly lesson.
A lesson in the law of resilience.
Efficiency is great. It's the goal until the unexpected hits. A system that wants to persist must deliberately allocate resources to maintaining diversity and redundancy. Even if it looks inefficient on the spreadsheet today, it's the price of survival.
Flow, openness, resilience. These three laws, they aren't just abstract principles, are they? The book connects them directly back to those mind capitals we've discussed before, the different forms of wealth.
Yes, absolutely. They're not just philosophical points. They are the operational health indicators for those capitals.
How do the map?
Well, think about it. The law of flow, conservation, and circulation directly governs the health of your material capital, resources, and your intelligence capital.
Yep.
Knowledge, models. Are you accounting for resource depletion? Is knowledge being shared and used or hoarded? That's flow. Law of openness, the need for connection and exchange with the environment, clearly governs the health of your network capital. Are you importing new information, new energy? Are you connected to diverse sources? That's openness. And the law of resilience diversity creates stability that directly relates to the health of your diversity capital itself. Are you maintaining a portfolio of options? Do you have variety in your skills, resources, approaches? That's resilience, ensuring you don't become a fragile monoculture.
So obeying these three laws is essentially how you maintain the health and vitality of the entire mind system, how you keep the generative engine running smoothly and persistently.
Precisely. They are non-negotiable physics of a healthy, intelligent, adaptive system.
This whole way of thinking, seeing the economy as this generative engine governed by these physical laws, it feels like it must completely change how you even do economics, right? The scientific method itself.
Oh, absolutely. It demands a fundamental shift, a paradigm shift, really.
Away from the old way.
Yes. Think about traditional economics, especially econometrics, for the past century. What has it been trying to do? It's been a science of inference.
Inference.
Meaning trying to deduce the rules of the game by looking at the outcomes. Collecting historical data, often sparse, aggregated data like GDP, and then trying to fit complex statistical curves to it. Trying to infer the underlying laws by observing the shadows on the cave wall, essentially.
And trying to explain the past.
Trying to find patterns in past behavior and assuming those patterns are the rules. The ultimate test was always, can my model fit the historical data? Can it explain what already happened?
Okay, so that's inference. How is intelligent economics different?
The book argues it needs to be a science of generation.
Generation. Creating, not just explaining.
Exactly. Instead of trying to work backwards from the messy, incomplete results, the historical data, you start with the fundamental building blocks. You define the microphysical laws that govern the agents within the system, which the book argues are these three laws: flow, openness, resilience.
You start with the rules.
You start with the non-negotiable rules derived from physics and computation. And then you compute what happens. You simulate the system. You let these agents following these laws interact, and you see what kind of macro reality emerges from those interactions.
You generate the outcome from the bottom up.
Precisely.
Yeah.
You build the system based on the known physical constraints and see if it behaves like the real world.
So the ultimate test of this whole framework isn't about explaining, say, the 2008 financial crisis after the fact with a clever model.
No. The ultimate test is, can we build a simulated economy based only on the principles of flow, openness, and resilience, and have it generate emergent properties like business cycles, price dynamics, innovation patterns, crashes, recoveries that look and feel authentically like our own complex reality?
If the generated simulation matches reality,
then we know we've likely found the actual underlying rules, the true physics of value creation and persistence. We've moved beyond just describing the game or keeping score.
we're understanding the rules well enough to maybe even build the game itself.
Or at least to understand how to play it sustainably. How to design a reality based on the laws that nature itself uses, not just the assumptions humans have made up.
That is, yeah, a staggeringly powerful idea, a completely different way to approach building a future that works. Okay, let's try to wrap up this deep dive into Chapter 7, the generative engine. If we had to boil down the main argument into one powerful sentence, I'd say it's this. The economy is a generative engine, a computational machine continuously turning chaos into usable order, and its ability to persist, its very survival, depends entirely on obeying the three non-negotiable physical laws of flow, openness, and resilience.
That captures it perfectly. And for you listening, the key takeaways, the really critical nuggets to hold on to from this discussion are: first, remember the economy functions like a giant AI diffusion model. It's constantly denoising the chaos of possibilities through countless small distributed actions. Every transaction, every idea is a step in generating order. Second, the law of flow is absolute. Value needs to be accurately accounted for, conserved, and it must circulate. Hoarding capital stops the learning process. It guarantees eventual failure, as Cahokia showed us. Accumulation without circulation is stagnation. Third, the law of openness. Isolation is thermodynamic death. Systems need to exchange energy and information with their environment to stay ordered and adaptive. Closure leads to stagnation and fragility, the harsh lesson learned by Sakoku, Japan. And finally, the law of resilience. Diversity isn't optional. It's mandatory insurance. Optimizing purely for short-term efficiency creates dangerous monocultures that shatter under unexpected stress, like the Gros Michel banana. Resilience requires embracing diversity.
Flow, openness, resilience. We've established these physical laws for a healthy, persistent system. We understand the physics the generative engine must obey, but understanding the laws isn't enough if we can't measure how well we're following them, right?
We need the right instruments. We need a new dashboard.
Exactly. We
Mhm.
can't steer this incredibly complex engine using broken old gauges like GDP, which just counts money changing hands. It tells us nothing about our actual capacity, our vitality, our resilience.
So we need metrics that align with these physical laws. And that's where we're heading next time. We're moving from the physics of value creation to the actual architecture of a vital system, the geometry of persistence. We'll introduce the essential framework the book proposes for measuring our collective health according to flow, openness, and resilience. It involves understanding the four interdependent forms of wealth that make up a system's true capacity.
The mind capitals again.
Exactly. All detailed in Chapter 8, The Mind of a Civilization. So please join us then for that crucial conversation.